Okay, well, I feel like we've made it out of the scary, scary place called Limits Involving Infinity, um, or subtitled 2 Days in Hell. Um, Infinity is just a freaky concept. And now we come to assignment 30, which is all about continuity. And continuity is really, really gentle. It We're going to have some very concrete rules. You're going to have to memorize these very basic rules, and it'll work every time. Uh, right. So, continuity. And by continuity, I mean, is the function continuous? Continuous. So what does it mean if a function is continuous? Well, this function is continuous at the point x equals a. This function is not continuous at x equals a. This function is not continuous at x equals a. So we've got these things called discontinuities. Here's a discontinuity. That's a jump discontinuity. A hole is a type of discontinuity. So a discontinuity is a place where the function isn't continuous. We could actually say, and this may be more helpful, y equals f of x is continuous at x equals c if the limit as x approaches c equals f of c. That's actually our definition of being continuous at a point. Now, we'll talk more about the implications of that statement in a moment, but first, um, I want to say something about endpoints. Endpoints are going to, no, I don't want to say anything about endpoints yet. I'm sorry. Let's just deal with this. To be continuous at a point. To be continuous at a point. So, we said to be continuous at a point, we need the limit as x approaches c of f of x to equal f of c. So what's the implication here? What does this mean? Well, this is the y value at x equals c. And this, well, remember we said a couple videos ago that the limit as x approaches c of f of x exists only if the limit as x approaches c from the negative side equals the limit as x approaches c from the positive side. So let's think about what we're saying here. We're saying, we're saying three things here. So here's the first thing we're saying. In order for f of x to be continuous at x equals c, there are three things that need to be true. One, f of c exists. If the point doesn't exist, then the function isn't continuous there. Look, at x equals c, the function doesn't have a value, and therefore the function is not continuous. Because f of c does not exist. Okay? All right. What's the second thing? Well, the second thing is that the limit as x approaches c of f of x needs to exist. But you know that in order for that limit to exist, it also means that as x approaches c from the negative side, has to equal the limit as x approaches c from the positive side. That's what's implied by that statement. These two limits have to not only exist, but they have to be equal to each other. And so when I look at this, and that's my x equals c, is this function continuous at x equals c? Well, f of c exists. I see the filled in circle, so I've made that requirement. But does the limit exist? Well, I'm approaching one y value from the negative side, and I'm approaching a different y value from the positive side, and therefore these won't be equal, and therefore that limit doesn't exist. So this is a case of f of c exists, but the limit as x approaches c does not exist, dne, okay? And you can use dne on the AP exam. So that's the second requirement. Now, there's a third one, and this is what we wrote down as the definition. We said, great, these both exist, but f of c has to equal the value of the limit as x approaches c of f of x. So let's take this situation. Here's x equals c. That's 2, and that's 1. Okay. Does f of c exist? At x equals c, the function is defined by that dot. It equals 2. The function equals 2 at x equals c. So we've got that one. That one's good. Now what about the limit as x approaches c? Well, as x approaches c from the negative side, we're approaching a y value of 1. As x approaches c from the positive side, we're approaching a y value of 1. So this limit does exist and is equal to 1. So the point exists, the limit exists. We've met those two requirements, but there's this third requirement. The value of the point and the value of the limit have to be the same. The value of the limit was 1. The value of the point was 2. Are they the same? They are not the same. And so this is not continuous at x equals c. Because, and you'll have to write some justifications for some of these, because while f of c exists and the limit as x approaches c of f of x exists, f of c does not equal the limit as x approaches c of f of x. Okay, so again, how do I write that justification? X equals c. I would say, and this is f of x, I would say f of x is not continuous at x equals c because while f of c exists and the limit as x approaches c of f of x exists, f of c does not equal the limit as x approaches c of f of x. Okay? Use your notation, use your language, justify your statement. Because I promise you on the next test, I'm going to ask you to explain why or why not the function is continuous or not at that point. Okay? So, point continuity. Continuous at a point. So let's think about continuous at a point. Let's take this one. Okay, so this is A, B, C. All right, am I continuous at x equals A? Is f of x continuous at each point. So, what can we say about x equals a? Does the limit exist? Am I approaching the same y value from both sides? Yes. While the limit as x approaches a of f of x exists, f of a does not exist, so f is not continuous at x equals a. What about at x equals b? Well, I say no, I'm not continuous. I will say that while f of b exists, the limit as x approaches b of f of x does not exist, right? The limit from one side is not the same as the limit from the other, so that limit at that point can't exist. Therefore, f is not continuous at x equals b. And here, well, at this place, we can say f of c does not exist, and the limit as x approaches c of f of x does not exist. My limits are headed in two different directions, and the point doesn't exist, so there's no way I can be continuous there. Okay? All right. Again, just want to stress we have a three-part definition of point continuity. Continuous at a point. And you need to be able to refer to these three parts in explaining why something is or is not continuous. So, at a point x equals c, f of c exists to the limit as x approaches c of f of x exists, which implies that the limit as x approaches c from the positive side equals the limit as x approaches c from the negative side. And then finally, f of c should equal the value of that limit. Okay? That's our three-part definition of continuous at a point. Now, what about, because there's two other types of continuity we need to consider, what about continuous on an open interval? From a to b. Okay, so we're not worried about being continuous at a or at b, just at all the points in between. There's a, there's b. Now, how many points are there between a and b? That's right, an infinite number of points. So, am I about to ask you to do the three-part definition of continuity at the infinity of all the points from a to b? No, I'm not. What instead I'm going to say is by observation. F of x is continuous on a to b. Okay, or by observation, f of x is not continuous on a to b. Okay, so it's a little easier for me to do continuity across an interval than trying to have the conversation about continuous at a point. Okay, well, except that here I am using my definition of continuous at a point, and I could say, hey, this is x equals c, and f is not continuous here at x equals c because f of c does not exist. Okay? All right, so last case. Continuous on closed interval, a to b. And the reason why this is a different situation is because now we're including endpoints. And why are endpoints tricky? Well, let's think about endpoints for a minute. Here's B, here's A. Now, we said if we wanted to be continuous at x equals b, we would need a couple of things to exist. We'd need f of b to exist. Yes, that exists. We'd also need the limit as x approaches b of f of x to exist. And remember, what does that imply? That implies that the limit as x approaches b from the positive side equals the limit as x approaches b from the negative side of the function. Well, this is an endpoint, and I've got a problem. Can I come from the positive side? No, that will never exist on the right endpoint. So, because endpoints bring a unique challenge, like here, I know that f of a exists, but does the limit as x approaches a from the negative side exist? There's no limit over here because there's no function over here. I don't know, it's not coming in from any direction. And because this doesn't exist, but this does exist, then we can't actually have the limit at that point. So we're going to have to define things a little differently when we deal with endpoints. And I encourage you to box this next thing in with highlighter because this is something that people forget. Okay, so continuous on A to B. 3 requirements. 1, continuous on the open interval from A to B. And we'll do that by observation. 2, we want that f of a equals the limit as x approaches a from the positive side of the function. Since a is the left endpoint, we can't come from the negative point. So we're actually going to define it this way. Only coming from one direction equals the value of the point. There's x equals a. It's an endpoint. F of a exists. I'm continuous on a to b, but the limit as x approaches a from the positive side does not equal the value of f of a, and so we would say, no, I'm not continuous at this endpoint over here. And we need one for the right endpoint, and so we're going to say that f of b has to equal the limit as x approaches b from the negative side, because b is the right endpoint. Okay, so we've got lots of continuity. We've got point continuity, continuous at a point. The point has to exist. The limit of the function at that point has to exist. And the value of the point and the value of that limit have to be the same. I know continuous on an open interval means that I'm continuous on all the points in between A and B. Continuous on the closed interval is not only continuous on the open interval, but because there are now 2 endpoints to consider, and endpoints, the limits can't come from both directions of the function because these are endpoints we're talking about, we have these special designations for left endpoint and for right endpoint. Okay, and so we're going to have to refer to these things when we justify our answers. All right, so let's do some practice. Here's a graph of f of x. 2. Okay, I've got closed circle, I've got open circle, I've got closed circle, I've got open circle, I've got closed circle, I've got closed circle, I've got open circle. And this is 1, 2, 1, 2, 3, 4. Okay, so let's have a conversation. Wow, we were just looking at graphs like this when we were talking about limits. That's right, and there's a reason for it, because now we're talking about continuity. And in order to have a conversation about continuity, you have to be able to talk about limits. So let's say, is f continuous. And why don't you see if you can explain if f is continuous at x equals 2? Why don't you pause the video and explain whether or not f of x is going to be continuous at x equals 2. Come back when you're done, or if you're not sure. All right, so here's what I think. I think f of 2 exists. And I think the limit as x approaches 2 of f of x exists. But is the value of the point the same as the value of the limit? Because that's the third part of our definition of continuity at a point. The value of the point has to be the same as the value of the limit. That's not true here, and so because f of 2 does not equal the limit of f of x as x approaches 2, f is not continuous at x equals 2. All right, great. That's what we want. We want a justification as well as the correct answer. Really, we really do want a justification as well as the correct answer. Okay, so how about now at x equals 1? Is f of x continuous or not at x equals 1? Why don't you try that one? Come back in a minute when you're done. Don't forget your justification. Okay, welcome back. Well, I know that f of 1 exists, but since the limit as x approaches 1 from the negative side does not equal the limit as x approaches 1 from the positive side, we know that the limit as x approaches 1 does not exist, so f is not continuous at x equals 1. Okay? Because I don't have a limit at that point, this piece is coming in towards 0, this piece is coming in towards 1. These limits are not the same. The limit at that point doesn't exist, and therefore, because the limit doesn't exist, f is not continuous at that point. Okay. How about at x equals 3? Is f of x continuous at x equals 3? Well, what do you think? Pause the video, give it a thought, write up a justification, and come back when you're ready. So I say f is continuous at x equals 3 because f of 3 equals the limit as x approaches 3 of f of x. The value of the limit exists because we're approaching 2 from both sides. The point exists, f of 3 is equal to 2. And since the limit equals the point, I know the function is continuous. Okay. What about at x equals 1? X equals 1. Am I continuous at x equals 1? Pause the video and give that one a try. Hi, welcome back. So, I said, since f of 0, oh, did I say 1? Oh, we already did 1. I hope you know I meant 0. Maybe you should try again if you did 1 a second time. All right, since f of 0 equals the limit as x approaches 0 from the positive side, since that's true, we know that f is continuous at x equals 0. Okay? What about at x equals 4? Am I continuous at x equals 4? No, I'm not continuous at x equals 4 because f of 4 does not exist. Okay, so that's the basics of continuity. Okay? Now, let's go a little further with this conversation. A point of discontinuity, continuity, is a point x equals c where f is not continuous. So let's see what we can say about f of x equals 1 over x. Here's a function. Is f of x a continuous function? And we say no. No, f of x is not continuous. Because, and what's our justification for that? Well, isn't there a point of discontinuity at x equals 0? Because f of 0 does not exist. We could also say no, because the limit as x approaches 0 for f of x does not exist. Remember, on this graph, one side heads to infinity, the other side heads to negative infinity. That limit doesn't exist. So I've got two reasons for saying that f is not continuous. Or we could say f is continuous everywhere except x equals 0 because of something like that. F of 0 does not exist. Great. What about this function? Y equals square root of x plus 2. So, when we think about this graphically, we have negative 2 here, and this function is continuous. Y equals square root of x plus 2 is continuous on its domain, because we know the domain goes from negative 2 to infinity. This part, we didn't think the function would need to be continuous over here because this part over here is not in the domain of that function. So we can either say this is continuous on its domain, or y equals square root of x plus 2 is continuous on negative 2 to infinity. We could say that. Okay, so let's get into discontinuities a little bit more, because we've got some certain types. Okay, we have removable and non-removable. Okay, and so when I think about removable, they look like this, or they look like that. These functions have removable discontinuities. That's not removable. That's not removable. And there's this really, really great one. Yeah, I think I can get you a graph of it, because I don't think you'd believe me unless I show you. sine of 1 over x, I think works. Zoom 6. Did I do zoom 6? Or I still have my axes turned on? Okay. Format, turn the axes on, and zoom, let's do trig. What's that all about? So let's zoom in there. Let's go -1 to 1. Huh, what's happening there? Let's get even closer. Let's go -0.1 to 0.1. See that? Is it scaring you yet? Quick, let's do -0.01 to +0.01. Oh my goodness. Yeah, and so what we say is that that is an oscillating discontinuity. So as we approach the point, this thing vibrates faster and faster. That's what we're seeing there, okay? So there are oscillating discontinuities. All right, so we've got these discontinuities. Why bother categorizing them? Oh, by the way, this is called a jump discontinuity because we jump from one to the other. And we know that when we see a vertical asymptote, that's called an infinite discontinuity. Okay. I don't know that you need to be hung up on memorizing these names. More important would be your ability to explain or justify why we have a discontinuity there. But I do want to say that while these are non-removable, there do exist some things called removable discontinuities. And the distinction between the two categories is how many points would I have to change to make the function be continuous? So with this function, I just have to redefine this point so it goes there. Or with this function, I just have to actually define a point so it fills that in. In either case, one point needs to be addressed. I'm only changing or adding one single point. But with these, how many points would I have to change to get this to touch this? Well, I have to change an infinite number of points. Can I ever get this to touch this by changing one point? No. No, I can't. And this, definitely not. So non-removable discontinuities, we have no possible hope of fixing, changing, whereas these removable ones, well, there's only one point, and if I defined that point differently, we could be continuous. So that's going to be the focus of our next video, finding continuous extensions for removable discontinuities. But for right now, I think I just want to ask you, some questions. Okay? So here we go. Here's our function f of x. F of x is x squared, let's way up there, is x squared minus 1 over x minus 1 for x not equal to 1, and 4 for x equal to 1. And I want to know this. Which statements are true? Okay, first statement. The limit as x approaches 1 of f of x exists. 2. F of 1 exists. 3. F is continuous at x equals 1. That's what we want to know. All right, so how are you going to think about this? Well, does the limit as x approach 1 for f of x exist? And in order for that to exist, we would need the limit as x approaches 1 from the negative side to equal the limit as x approaches 1 from the positive side of the function. Hey, by the way, if you write down this, I don't know what the hell you mean, because it's got to be the limit of something. It's got to be the limit of a function. When you leave those out, I mark wrong. I don't know what you're talking about. I think you're starting to, drink insane juice in the morning and you don't get any points. So not only do you have to tell me what we're approaching, but you have to say the limit of what. All right, so what can we say here? Does the limit as x approaches 1 of f of x exist? How can we know that? Well, let's take a look at f of x for x not equal to 1. It's this rational function. Okay, what's that rational function look like? Well, the top factors as x minus 1, x plus 1, and then I could do some canceling. So this graph is going to look like x plus 1 for all x's except at x equals 1. Because I cancel these factors, I have a hole in my graph at x equals 1. But that I'm not so worried about right now. I'm just considering, is f of x, does the limit of f of x exist as x approaches 1? Well, the limit from the negative side is 2, and the limit from the positive side is 2. And since the limit of this function is approaching the same value from both sides, then yeah, 2 does equal 2, and so yes, the limit as x approaches 1 does exist. But look at this. I know that f of 1 exists because they tell me f of 1 is equal to 4. So that one works. Okay. What about is f continuous at x equals 1? The point exists, the limit exists. Is this function continuous at x equals 1? Okay, so here's what we say. We say, no, f is not continuous at x equals 1 because the limit as x approaches 1 of f of x does not equal f of 1. Okay? We need to be able to think about stuff like this. Okay? What helped me here? Thinking about the graph. What helped me here? Knowing this limit definition. What helped me here? Well, reading the piecewise function helped me there. And for this part, this Roman numeral 3, I had to know my 3-part definition of continuity of the point. So we need limits to help us figure out continuity. And we're going to need continuity to help us figure out slopes at points. Okay, so let's go further. Here we go. F of x equals x squared plus 5x plus 6 over x squared minus 4 is continuous. This is Roman numeral 1. Is continuous on negative infinity to infinity. Roman numeral 2 has a removable discontinuity at x equals 2. Has an infinite discontinuity at x equals 2. All right, so what do we think here? Well, I know that this factors as x plus 2, x plus 3, over x plus 2, x minus 2. Hey, remember all those times when your Algebra 2 teacher said you gotta learn to factor a difference of squares? Yeah, because when you do these problems, you have to be able to do this in A, you have to be able to do it, and B, you need to be able to do this quickly enough so that it doesn't take you forever just to get to the point where you can start talking about the problem. So what do we know here? We know that there's a hole at x equals -2, and we know that there's a vertical asymptote at x equals +2. So I go with this one. F of x has an infinite discontinuity at x equals 2. Does it have a removable discontinuity anywhere? Yes. At -2, we have a hole, and a hole is a removable discontinuity. Okay. Next. Something flipping pages has eluded me at this point. Okay. I love this language for this next problem. Consider the function f of x equals x squared minus 2x over x to the third minus 9x on -5 to 5. Okay? List any points of discontinuity. Well, discontinuity. This is a rational function. Rational functions have holes. Holes are points of discontinuity. Rational functions can have vertical asymptotes. Those are infinite discontinuities. Does this function have any vertical asymptotes or any holes on it? Well, if I factor the top, I've got that. If I factor the bottom, I'm taking an x out, I've got x minus 3 and x plus 3. Okay, look. There is a removable discontinuity at x equals 0, and there are infinite discontinuities at x equals 3 and x equals -3. Okay. Next. Happy notes. There was one more set of stuff I wanted to look at with you. Where is set of stuff? Well, maybe I'm the one getting crazy insane juice this morning. Because I don't see anything else, so I'm going to say, well, that's all we got. Okay, that's all we got. It's very strange, because I could have sworn. I'm going to look one more time. Yeah, that's all I got. All right, so tonight's homework, continuity. It will be gentle. You will be happier. Don't hide from it. Embrace it. Assignment 30 goes with this video. All right, take care, everyone.